All right, what we're going to look at today here for the second part of 2.6 is we're going to make some generalizations first about the behavior of some rational functions. Okay, we studied some rational functions already. Most of the ones that we've studied so far have been the least complicated, if you will. Okay, ones that can be written as transformations of 1 over x. Okay, the ones we're going to look at today are going to be a little bit more complicated and have some different behavior that we're going to see. Okay, but ultimately, if we have the graph of f of x over g of x, okay, some polynomial over some other polynomial. And I want you to notice that there's a couple of the key things we're looking at here is, first of all, the f function here has degree n, and the g function has degree m. So these could be any degrees. N and m could be anything. They could be degree 0, they could be degree 1, 2, 3, 4, etc. Okay, so we're going to make some generalizations about behavior, okay, when we have different degrees on top and different degrees on bottom. Okay. Now keep in mind that n and m could be equal to each other too. Okay, they could be both the same degree. But ultimately, here's the deal. Okay, these types of functions are always going to have similar n behavior based on the degrees of the top and bottom. Okay, if n is less than m, okay, so in other words, if the degree of the top is less than the degree of the bottom, okay, then the n behavior asymptote is a horizontal asymptote y equals 0. Okay, so here's an example of one that would fit that bill if I had something like, let's say, 2x plus 3 over x squared plus 4x plus 5. Okay, right. That would be an example of n being less than m. The top degree is less than the bottom degree. Therefore, if I were to look at a graph of this, we should expect that there's going to be a horizontal asymptote of y equals 0. Okay, remember a while back when we studied these the first time, you asked me, is there an algebra way to know that the range here is going to not include 0, that there's going to be a horizontal asymptote there? Yes, here it is. Okay, it's all about what the degree is on top and bottom. So if we graph this, we would see a horizontal asymptote in both directions, okay, of y equals 0. Therefore, we'd also say that the limit as x approaches 0 for this type of function, alright, I said 0, but I meant infinity, is 0. And also the limit as x approaches negative infinity for this function is also 0. So when we have that situation where the top degree is less than the bottom degree, okay, we have 0 as our two n behavior limits, okay, which again also corresponds to the fact that we have a horizontal asymptote at y equals 0. And just as a preview, okay, this really the reason why this is the case is because if you look at this linear function on top and you look at the quadratic function on the bottom, okay, in terms of growth rates, the quadratic function is going to grow a lot faster than the linear function is going to grow. So if I were to put a number like 5 in there, okay, this number on top might not be that much smaller than the number on bottom, but if I put 5 million in here, this is going to be, you know, a pretty big number, but if I put 5 million into this, it's going to be outrageously big. True? And keep in mind, if I have a big number on the bottom and a small number on top, okay, and I divide them, I'm going to have something close to 0. So as we let x get bigger and bigger, or in the case of smaller and smaller going left, okay, this is going to go to 0 because the bottom function is going to grow faster than the top function. Okay. Similarly, if we had something like our parent function 1 over x, same deal. Okay, 1 doesn't grow, but x gets bigger as it goes to the right. This is going to be 1 over big numbers, which is going to create 0 algebraically, which hence this is why we have a horizontal asymptote of y equals 0. Okay. Now, if the n and the m are equal to each other, okay, then the n behavior asymptote is a horizontal asymptote, and it is y equals a of n over b of m. And notice, what are those two things? A of n and b of m, those are the leading coefficients. So as an example, if we had something like, let's say, 4x squared plus 2x plus 3 divided by 3x squared plus 5x plus 9, okay, we would recognize that the degrees are the same. The n and the m are both 2 here in this case, and therefore this one's going to behave like y equals leading coefficient of the top divided by leading coefficient of the bottom. So therefore the horizontal asymptote in this case is going to be y equals 4/3. And if you were to graph this and graph this, okay, would that be fairly clear by looking at the graph that we have a horizontal asymptote at y equals 4/3? Absolutely. Okay. And again, we would say the limit as x approaches infinity of this particular function would be 4/3, and the limit as x approaches infinity, negative infinity that is also 4/3. So both of our limit statements would correspond to our horizontal asymptote, okay? And we can move on from there. Now, ultimately, the most difficult situation to deal with is where we have n greater than m. Okay? If the top degree is higher than the bottom degree, okay, then the n behavior asymptote is the quotient polynomial function when we do the division. Okay? All right, so a couple things, we'll do some examples of those in a minute, but ultimately we're going to take those two, we're going to divide them, and whatever the quotient is like, okay, that's how the function is going to behave at infinity. Okay? And notice also there is no horizontal asymptote. Okay? If we have a degree on top bigger than the degree on the bottom, okay, you will not see a horizontal asymptote. Okay? So like I said, we're going to see some examples here in just a minute of that type. Okay? Okay. All right, a couple other ideas about the graphs of a rational function. Okay, once again, if we have a rational function, any polynomial over any other polynomial, okay, regardless of degree, there are a couple of characteristics that we're always going to have. Okay, number two on this, besides the n behavior situation, okay, we'll have vertical asymptotes. These are going to occur at the zeros of the denominator, okay, provided that the zeros are not also zeros of the numerator of equal or greater multiplicity. Now that sounds fairly complicated, okay, but what it boils down to is this. Okay, we're going to have vertical asymptotes wherever the bottom has zeros. So for instance, if I had something like x plus 3 and x minus 3 on the bottom, we should expect vertical asymptotes at -3 and +3. Okay, unless, okay, and this is something else you guys asked me about earlier, okay, is there a way to tell algebraically that there's going to be an asymptote or a hole? Because we know the other alternative here is that these could be asymptotes or they could be holes. Okay, if the top factor to say x plus 4 and x minus 3, okay, that x plus 3 then, okay, is an asymptote because that's not a zero of the top. Okay, whereas this one, x minus 3, would make 3 a zero of the bottom. It's also a zero of the top. Okay, and remember this said provided that the zeros are not also zeros of the numerator. So in this case, here's the deal. If we have one of our zeros of the bottom actually cancel out with one on the top, okay, that's the situation that's going to create a hole. Okay, so if it does not cancel out, then that situation is the asymptote. Okay. So can we tell algebraically? Yeah, we can factor the top and we can factor the bottom. And if one of the bottom factors cancels out, okay, that means there's going to be a hole in the graph. So if I were to graph this right now, we would see a vertical asymptote at -3. And at 3, we wouldn't see anything because there's a hole in the graph. Okay, we would see it on the table, okay, but we would not see it on the graph because your graphing calculator doesn't show holes very well. Okay, so that's the key issue here when we're looking to tell whether these are asymptotes or holes, is that if we can get one to cancel out, okay, then it is a hole on the graph and not an asymptote. Okay. All right, and then on the third thing here, another characteristic of rational functions, okay, the x-intercepts are always going to occur at the zeros of the numerator, okay, which are also not zeros of the denominator. Okay. So in this particular case, we might say, okay, well, -4 and 3 would be x-intercepts. However, okay, if that -3 cancels out with something on the bottom, then the only one is -4. This one would not be. Okay. And then finally, the y-intercepts, just like any other equation, when we put f of 0 in, okay, that's going to give us the y-intercept. So if I were to put a 0 in for x, I'd get -12 on the top, and I would get -9 on the bottom. And that would make 4/3 if I simplified it. So we'd have a y-intercept in this case of 4/3. Okay. So again, what's nice is that these characteristics that we're talking about right now are going to be the characteristics of all rational functions. Okay, all rational functions have to follow these rules. Okay. Questions so far? All right, so let's take a look at a couple of examples that they have here. It says find the asymptotes of the function f of x equals, and this is our function. So let's start out with vertical asymptotes. And conveniently, they already factored it for us. Okay, it might not be factored. You might have to do the factoring, but in this case, they factored it for us, which was nice of them. So let's talk about this one right here. Is this going to be an asymptote if I have x plus 1 down here? There's nothing to cancel it out with on top. True? So therefore, yep, that would be a vertical asymptote, x equals -1. What about this one? This one cannot be canceled, so it would be. Okay, notice the order that I'm doing this in. I'm finding the vertical asymptotes first, okay, and then I'm going to find the horizontal asymptote second. Okay. Now, again, the horizontal asymptotes are dictated by the degrees of the top and the bottom. So what's the degree of the top? If I were to expand this, it would be quadratic, wouldn't it? So it would be degree 2 up here. If I expanded this, it would also be quadratic. So this means that n and m are equal to each other. So that means we're going to have a horizontal asymptote at y equals leading coefficient of the top divided by leading coefficient of the bottom. So if I were to expand this and then multiply it by 2, wouldn't this be the leading coefficient of the top? And if I were to expand this, wouldn't the leading coefficient be 1? And therefore, what would my other asymptote be? 2. Okay. Got 2 on top, 1 on the bottom. 2 over 1 is 2. Now, if I were to change this to a graphing problem, I would want to do exactly those same things right there. I'd want to find the asymptotes first. Okay, I'd want to graph the asymptotes. And then I got y equals 2. Okay. And that would set up a bunch of different areas here where I might have some actual curve behavior. Okay, and the question is, how do I know then what the curve looks like in between these asymptotes? Okay. Well, I would want to make an XY chart, and just like I did with my other ones I did on Friday, okay, I would want to have 3 points over here, 3 points in here, 3 points in here. So really we need 9 points. Okay, if it's a calculator problem, you can get them with the calculator, but ultimately we need 9 points, and hopefully we could test that behavior. Okay. Did I put a +5? Sorry. 1, 2, 3, 4. Sorry. So it would look like that. So I'd want 3 points in this group, 3 points here, and then 3 points over here. Okay, and when we get that done, we could have a reasonable picture of our curve. Okay. Questions so far? All right. Let's take a look at another one. Okay, this one says same deal. Find the asymptotes, but this time it asks us for the intercepts also. So let's start with, let's say, vertical asymptotes. So this one would give me x equals 2. It can't cancel out with anything on the top, so we would have x equals 2. Same thing here. This one does not cancel, so we'd have x equals -3. Okay. Now, how about our horizontal asymptotes? What's the degree of the top? 1. Degree of the bottom? 2. So this means the bottom degree is larger than the top degree, which means the bottom grows faster, which means that ultimately at infinity this is going to go to y equals 0. Okay. So y equals 0 would be the horizontal asymptote for this particular case. And again, for graphing, I'd graph my 2 horizontals, my 1 vertical, and then I'd plot points in each of those regions. So once again, if I have 2 horizontal asymptotes, I would need 9 points essentially to get a reasonable idea of what it would look like. Okay. And then we could go from there. Now, how about intercepts? Okay, the intercepts, start with the x-intercepts. The x-intercepts, they told us that the x-intercepts are going to come from where the top equals 0. Because remember, if a fraction equals 0, okay, the only way a fraction can equal 0 is if the top equals 0. So if we set the top equal to 0, we're going to get x equals what? X equals 1. And once again, that does not cancel out with anything on the bottom, so that is going to be a legitimate answer for us. What about the y-intercept? The y-intercept, we plug in 0 for x, so we'd have -1 on the top, and we'd have -6 on the bottom, 0 here and 0 here. -2 times 3, so it would be -1 over -6, which would be what? 1/6. So those would be the 2 intercepts. And those would be good points also to plot if we were asked to graph this. We'd want to plot those 2 points also, so those are important points, the intercepts as well. Okay, questions so far? The x-intercept is going to come from when the top equals 0. Okay, as long as the top doesn't get canceled by one of the bottom factors. So if I said x minus 1 equal to 0, that would give me x equals 1. Okay. So we're just going to set that top equal to 0.